Thank you very much. And well, so I would like to thank the organizers for inviting me. And well, I would love to tell you that I will present you some super interesting new results, but last year I had a terrible disease which is called teaching, so I didn't have much time for doing research. So you may be wondering what this title means. Well, maybe you don't, but I do. So at some point it made sense to me, so let me try to explain you. So in reverse mathematics, we like to talk about the big open question about those stable Ramsey theorem for pairs implies cohesiveness. And well, in reality, who cares about this big question, right? Because it's very technical. Stable Ramsey theorem is not a natural statement, and reverse mathematics is about natural ordinary theorems. So the reason we care about this question is because it's at the boundary of what we know, and it's at the boundary of a technique that we have, which is called that we call Mathias forcing and the CJS arguments. And this Mathias forcing and the CJS argument has been pretty good at answering a lot of questions about Ramsey theory. And so we would like to know whether, we would like to understand why this fails for this particular question. And so in general, I'm not really interested in the actual answer to a question in reverse mathematics. I'm more interested in our ability to answer questions. And so this is where the title comes from, because it comes from the well-known proverb, give a man a fish, he will eat for 1 day, or if he eats slowly. And otherwise, if you teach him to fish, then he will have fish for his whole life. Well, and so for people who are vegetarian, you can make the same version with carrots. You give a man a carrot, and otherwise you teach him to fish, and he will have carrots for the whole life, whatever. And so the whole idea is Mathias forcing the true notion which will help us to answer all questions about Ramseyan principles, and in particular is the big open question, a witness of failure of Mathias forcing, or is it just because it was more complicated but the usual technique will still apply? So we have examples of open questions which were solved by very subtle and technical applications of the standard technique, but which still were solved. So this is the big question for me. It's not really about the actual answer of this 32-2 versus co. It's more about how we found the right framework for answering all questions. So this is basically the subject of my talk. So when you look at ordinary theorems from everyday life, a lot of them can be formulated in terms of problems. For example, if you take the intermediate value theorem, so it tells you that given a continuous function which changes its sign over an interval, you can find a real in which it would be equal to 0. And so you can really see it as a problem where I give you as an instance a continuous function which changes its value, and in a solution to this problem would be a 0 of this function. And for example, Koenig's lemma also tells you that even given an infinite finitely branching tree, you can always find an infinite path through it. And when you look at these theorems seen as problems, when you look at their proofs, you see that some of them are more effective than others. So for example, the intermediate value theorem, if you have access to the continuous function, you can compute from this continuous function, you can compute a 0 by the trichotomy arguments. While for Koenig's lemma, for example, we cannot really compute it. You can construct it by picking the roots, and then we know that one of the sub-branches has to be infinite, so you pick this one, and then you continue, you iterate. But you cannot know computably which one will be infinite. And so actually, you can build a computable finitely branching tree which has no computable path. So we can see that some problems are easier than others in terms of computability theory. And there are many ways to compare problems, because when you see that some are more complicated than others, we can say yeah, so what if I were able to solve this problem, which other problems would I be able to solve? So this is, we have many notions of reductions, and I'm going to talk about one framework, which is reverse mathematics. So the goal of reverse mathematics is to try to find the optimal axioms to prove ordinary theorems. And by ordinary, I mean like theorems that we see in everyday life, that we study in class, that we use in industry, not the last set theoretic results under the assumption of high cardinals, because these are outside this framework. I don't say that these are not interesting, but just not within this framework. And so to compare theorems, we use a very weak Bayes theory, which informally captures computable mathematics. So I will make it formal later. And so in some sense, if a theorem is provable inside RCA0, this theorem is computably true in particular, which means that any computable instance of your problem has a computable solution. And you can compare, you can say a problem is harder than another if the first problem implies the other within this Bayes theory. And since the Bayes theory captures computable mathematics, it means that you have some kind of computable process to obtain the other problem given the first problem. So more formally, so we work within the subsystems of second-order arithmetics, which means with integers and sets of integers. So the reason is that empirically, so there have been some studies which have shown that a lot of theorems can be formalized in a quite natural way, or expressed in a quite natural way within the language of second-order arithmetics. And the use of this second-order arithmetics has a good advantage is that we can talk about a notion of computability, the effectiveness of your problems. So you have to define the axioms at the first order and the second order. So at the first order, we have Robinson arithmetics, which is basically Peano arithmetics where you remove induction. So it just ensures that the integers will behave quite well. At the second order, so you have the delta 01 comprehension scheme, which gives you, it's kind of set builder, so you can add new sets to your model. And the fact that you restrict to delta 01 schemes means that you allow to have new sets which are built computably from the previous sets in the model. So you close under the kind of computable reduction. And then you have the sigma 01 induction scheme. Oh, there is two sigma 01, but okay. Where it's, so I won't go too much into the details. The reason we restrict induction is because the sigma 01 induction scheme is equivalent to some bounded delta 01 comprehension scheme in some sense. And so we can think of it as restricting the complexity of the finite sets. Okay. And so since the start of reverse mathematics, so which was initiated by Harvey Friedman and pursued by Stephen Simpson, there has been this big observation that when we take ordinary theorems, a lot of them satisfied a structural observation that there are 5 big systems. So RCA0, which is the weakest, but you have weak Koenig's lemma, ACA0, ATR0, and pi11 comprehension. So that when you take a theorem randomly, you are, in the naive sense randomly, you are likely either to be provable in RCA0 or equivalent modulo RCA0 to one of the 4 other subsystems. So this is really a strong structural observation about mathematics. And so, of course, there is the question whether this big 5, so they are called the big 5, this big 5 phenomenon, is it a deep observation, or is it just some kind of bias because we just look at some particular theorems? And there is a famous counterexample to this phenomenon, which is Ramsey theorem for pairs. So I will explain what Ramsey theorem for pairs, but it was historically the first theorem which was probably like incomparable, so which was not within the big 5, and actually it's not even linearly ordered with the other subsystems. So what is Ramsey theorem? So given I define the notation for given a set X and N to define the set of unordered n tuples of elements over these sets. And then we can define a K coloring of this set of n tuples, which is just a map from the n tuples to k colors. And then we say that a set, an infinite set of an infinite subset of X is homogeneous for the coloring if all the n tuples over this set have the same color. And so Ramsey theorem for n tuples and k colors tells you that if you have a k coloring of the n tuples over the integers, then you can find an infinite homogeneous set. So for the case n equals 1, you just have the infinite pigeonhole principle. So there is just one subtlety, is that here, given a k partition, a solution is not necessarily one of the two parts. It's an infinite subset of one of the parts, okay? Which makes the statement much weaker. When you look at pairs, this can become a statement about graphs. So if you have, it tells you that every k coloring of the infinite clique, you can find an infinite monochromatic subclique. So here, well, I didn't have enough space for drawing an infinite clique, but you can infer how it generalizes. And so it was a long-standing open question whether Ramsey theorem for pairs, so which was known to be provable in ACA0, it was not too difficult, proven by Karl Jokusch, whether this implies back ACA0. So ACA0, I did not define it. It's the arithmetical comprehension axiom, so which closes the model by the arithmetic comprehension axiom. And you can think of it as the statement of the existence of the Turing jump. So for every set, the jump of the set belongs also to your model. And Sitapen proved eventually that Ramsey theorem for pairs and two colors, so the number of colors doesn't matter, does not imply ACA0. And for this, he preserved some weakness property, so I will explain what a weakness property, using a proto version of what I call the CJS argument. I will also explain what the CJS argument is. So weakness property is just a collection of sets which is downward closed under the Turing reduction. So it's almost a Turing ideal, it's just that it's not closed under the join. So basically you have a lot of weakness properties. I guess we just call it lowness properties usually. So being low is a weakness property, not computing a fixed, so not being above the cone of a fixed set is also a weakness property of being hypermewn free, so just another name for lowness. And we say that, so given the weakness property, and given a problem which is expressed in terms of instances and solutions, you can say that it preserves this property if for every context Z which is inside this weakness, and every Z computable instance, you can find a solution so that join Z, so still within the context, it will stay within, it will still satisfy the weakness property. And thanks, if P preserves W, so the weakness property, it's easy to build some Turing ideals in which P will hold. And if Q does not, then we can also create a Turing ideal in which P will hold but not Q, and so we have a proof over RCA0 that P does not imply Q. So it's a very convenient way of building models for separating notions. And so the way Sitapen proved the separation was using the weakness property of saying the set of X so that X is incomplete, so does not compute the halving set. Actually, he proved something stronger. He proved that given any non-computable set and given any computable instance of Ramsey theorem for pairs, so that is any two coloring of the pairs of the integers, you can find a homogeneous set which still does not compute this non-computable set. So it's not only for the halting set, but for any non-computable sets. Okay. It's by forcing. It's a forcing proof. Yeah.
I mean, in logic, you distinguish there's a syntactical version and then there's a semantical version. And there was a famous theorem by Gödel in Pika1, whatever is deducible is also derivable.
Yeah.
So what do you use here?
So here, since I build a model of one which is not a model of the other, so it's the semantical approach. Yes. So for and so this was the first example of a huge range of new results about Ramsey theorem and variants of Ramsey theorem, and for this, so Sitapen theorem used two main tools, which was Mathias forcing and an original version of the CJS arguments, and which has been very successful. And now if we look at the more modern reverse math zoo, so the big five phenomenon has totally disappeared within the various statements. And a lot of them come from Ramsey theory. And this zoo is absolutely not up to date. So it was many years ago. So we often talk about the remaining open questions, but we don't talk enough about the success of the current techniques for answering all questions. So since the start of this analysis, so a lot of separation have been done. And the big observation is that basically when you define two variants of Ramsey's theorem, then they will be incomparable. Or one will be strictly weaker than the other, but so it's really chaotic. But since then we have a lot of results, and so we can start to make some big observations about these results. And the first one is, usually when we prove that some principal P does not imply some principal Q, we make it by forcing, and we could make, so to be the model of P, which is not a model of Q, we have to be able to make simple solution to P. And so we use forcing, and this forcing may depend on Q, but actually, empirically, the notion of forcing still is always the same for P, independently of Q. So this is an observation that, at least for the principle we look at, there seems to be some canonical notion of forcing associated to it to build solutions. And each time we make a separation, we still use the same notion of forcing, we just give a different argument why the generic will be weak enough for the new weakness property, but we still use the same canonical notion of forcing. So a lot of separations are obtained by using some weakness properties. So for weak Koenig's lemma does not imply ACA naught, uses cone avoidance, of Erdős-Moser does not imply Ramsey theorem for pairs, it's preservation of two hypermeunities. So there are a lot of, for each two principle, you can design a lowness property which will be preserved by one and not by the other, and it's the way you make a separation. So and this is much more informative than just the separation, because now we understand why it's separated. We understood better the computability theoretic properties underlying the separation. So what do I mean by a canonical notion of forcing? I don't have a precise answer. It's just informally the notion of forcing is canonical for a problem if whenever you can prove a property, a lowness property for this problem, we can show that it is preserved by the problem, then it can be proven using the canonical notion of forcing. So this would be informally the idea. Of course, to make it work, we have to restrict to some classes of properties. And first of all, there are basically two main classes of properties. There are of weakness properties. There are the effectiveness properties, or what I call effectiveness, which are properties for which you need the whole construction to be effective. For example, for lowness, to build a low solution, you need to make a construction computed by the halving set where you can control the jump. So the overall construction has to be effective. While for genericity properties, which are obtained by, usually properties which are obtained by notion of forcing, you don't need the overall construction to be effective. For example, for cone avoidance, any sufficiently generic for Mathias forcing will be cone avoiding or whatever. So usually an effectiveness property is countable, because since the overall construction has to be somehow effective, there are only countably many algorithms. This yields countable classes of lowness. And for genericity, well, I don't have, so yeah, I expect them to be uncountable, but I don't have any precise definition of what is a genericity property. It's informally a genericity, it's informally a property which can be obtained by notion of forcing. But one particular class of genericity property is what I call an open genericity property. So this direction is a work with is joint work with Denis. So we say that P is an open genericity property if it is the set of reals which do not compute a fixed closed set in the bare space. And these classes of genericity properties is already sufficiently general to express almost all the properties we have been using in reverse mathematics for proving separations. So this may seem quite restrictive, but actually this covers a lot of preservation properties. And as an example, but there are other examples, we can show that the notion of forcing with pi01 classes is a canonical notion of forcing for weak Koenig's lemma if we consider with respect to the class of open genericity properties, which means that if weak Koenig's lemma preserves some fixed open genericity property, it can be proven without loss of generality with a forcing with pi01 classes. So this one is very simple, but we can see other. We are currently studying other examples, and so I think this is a kind of direction which helps understanding better why the techniques work so far. We try to understand whether there is a natural notion to build solution of your principles. So the second big observation is that when we consider Ramsey type statements, and I will define what a Ramsey type statement is, or at least try to define it, well, we have quite a minimalistic framework to analyze the computability theory of these statements. And this framework is just the use of Mathias forcing with what I call a CGS arguments. CGS stands for Scholak, Jokusch, and Slaman. It's named after the seminal paper, The Strengths of Ramsey theorem for pairs, and which made a heavy use of these arguments. Previous slide. So
you get a closer in pair space.
Yeah, so that is you just have like, it's a closed set in the bare space. It doesn't need to be compact. Yeah, so you take a closed set in the bare space, and then you look at the set of all x, so that x does not compute any member of your closed set. This is a weakness property. And this, you can express a lot of things like that. You can express, so Kohn avoidance is just you take C to be the singleton, your set A. So then it's just the collection of sets which do not compute your set A. But you can define also preserving one hypermewn function. So given a hypermewn function f, you can define the closed set C of all the function g, so that g dominates dominates f. And then, if you do not compute any member, it means that you preserve hypermeunity and so on. So a lot of almost all the notions we have been using so far in the separation in reverse mathematics are particular instances of open genericity properties. And so we try to explain why each time we have been able to use the same properties. Because each time we design a new notion, actually we show that weak Koenig's lemma preserves it, and we use always forcing with pi01 classes. So we'd like to say it's normal. It's because we can always do that. So here, for Ramsey type statement, we have some kind of minimalistic arguments. But let's make first precise the notion of Ramsey type principle. So the appellation Ramsey type has been used for a long time, and nobody gave any precise definition. And the one I give it's just to serve my purpose, but it's not a canonical definition. It's not standard. So I extend the notation of tuples over a set to the infinite tuples over a set. And I say that a problem is of Ramsey type if for every instance, so the set of solution is downward closed under the subset relation. That is, if you have a solution, then any infinite subset of your solution is again a solution. And it's dense in the sense that for every infinite set, you can find an infinite subset which is a solution to your instance. So this is what it means. And Ramsey type principle have a very nice property, is that we can solve multiple instances simultaneously, in the sense that given two Ramsey type problems, if you take an instance of the first problem, an instance of the second problem, you can create an infinite set which will be a solution to the two simultaneously. And actually, you have this operator which says, which basically is this problem. Given two problems, we can define the intersection problem, which says, given two instances, I want some set which is a solution to both simultaneously. This is, again, a Ramsey type problem. This satisfies the two previous properties. And we are going to use this a lot. So now I would like to exemplify the CJS argument to, I guess it's the best way to explain what the CJS argument is. And so I'm going to prove the following theorem, which is given a set S, which is non-computable, then for every set A, so with no computability restriction at all, you can find an infinite subset of A or its complements, which does not compute this set S. And so for this, we are going to use, so the input is S and a two partition. So I see my set A as a two partition of the integers, and I want to build an infinite subset of one of the parts, which still does not compute S. And for this, I'm going to use some Mathias-like notion of forcing. So the idea with Mathias' notion of forcing is just that you are building two finite objects because you don't know in which side you are going to build your solution. You don't know whether it's a subset of A or the complement. So because you can't make a choice, you are building two objects at the same time. So you make one for color blue, which is inside A, and for red for inside the complement of A. And so these represent the finite initial segment of the infinite object you are building. And then you have an infinite set of integers, which is a kind of reservoir. It restricts the next element you are going to take to add to F0 and F1. That is, whenever you add elements to F0 and F1, it has to come from X. And with time, the reservoir will get smaller and smaller. So formally, you have F. So F is finite, X is infinite. We want that the maximum of F is smaller than the minimum of X just for continuity arguments. And then we add some extra condition, which is that the reservoir does not compute your set S. This is some extra condition. And you want that F0 is a subset of A and F1 is a subset of the complement of A. So a condition really represents a partial approximation of the object you build. So you build basically two objects. And the extension is the one you can expect. That is, you increase the set F to obtain a set E. And the elements so you restrict more the reservoir. And the elements you add to F to obtain E come from the initial reservoir. So this is the definition of the extension. And informally, you can really see the interpretation of such a condition as the set of all pairs, so that they have the same initial segment as F, and their elements are included. Their remaining elements are included in the reservoir. And we have this property that when a condition extends another one, then it restricts the denotation. Okay. So this is quite standard definitions. And then we can define a notion of forcing. So what it means for a condition to force a property. And so we are going to use a very degenerate forcing relation, which say that the condition forces a property if the property holds for every object in the denotation. That is, for every candidate, it has to hold. And so we know that if for every candidate it holds, then whatever we are going to do later, the property will hold. Okay, so let's recall our goals. So we have as an input a non-computable set, and we have a two partition. We want to build an infinite subset of one of the parts, so we are going to build two objects, and which still does not compute the set. So we want the following requirements. For every pair of functionals, so phi E0 and phi E1, we want to satisfy the following disjunctive requirements. Either phi E0 is different from S, or phi E1 is different from S. And by the standard pairing arguments, if this is satisfied for every pair of integers, then we'll have that G0 does not compute S or G1 does not compute S. Because suppose it fails, suppose that G0 compute S by some E0, then for every other E1, since this requirement is satisfied, we'll have that phi E1 with oracle G1 is different from S, and so we have that G1 does not compute S. So this is sufficient. And so for this, more formally, we just have to ensure that the following set is dense. So dense just means that for every condition, you can find an extension which belongs to this, which satisfies this property. And here, this is just the set of things for which either I can find a witness for which I halt on the wrong value, or I can find a witness of partiality, so on the left side, or I can find an input on which I halt on the wrong value on the right side, or I can find an input which witnesses partiality on the right side. So these are the 4 possible cases. So imagine that we are in a perfect world, and that the formula, given a condition and given x and n, the formula asking, is there an extension so that I can force G0 to halt on input x and output n? Imagine it is sigma 0, 1 relative to x. Actually, it is not, but imagine it is. Then define the class of all pairs x and n such that this formula holds. That is, so that I can find an extension for which I can force my functional to halt on x and output n. Then this set is XCE, so it's computably enumerable in X, because it just tells you, well, because by assumption. Then consider this set. So we have 3 cases, and one of them will be impossible. In the first case is there exists an input so that, and there exists a wrong value so that I can find an extension for which I force to halt on the wrong value. Then it's good, because you take this extension and you force to be different from your set S. In the second case, well, there exists an input and the good value which do not belong to your class, which means that actually so that there is no extension forcing you to halt on the good value. Then it means that you force already either partiality or to halt on the wrong value. So this is also good. And in the last case, it is an impossible case. In the last case, well, for every x, when you have a pair x, y which belongs to C, y has to be the good value by failure of the sigma 1 case. And by failure of the pi 1 case, for every x, there exists a y so that xy belongs to C. So which means that for every x, you can find a y which belongs to C, and this y has to be the good value. But then you can compute in X the set S, because you given X, you just wait until some V, so that the pair XV happens in C, where for any V, and you know that this V has to be the good value, so you just output V. So this is a way to X compute S. But X, by assumption, does not compute S, so you have a contradiction. So all of this was under the assumption that your formula was sigma 01, having an extension forcing to halt on an input for a particular value. In reality, this is not the case. It's not sigma 0 x1. Why? Because if you translate the formula, is there an extension so that I force to halt on input x and output n? Formally, this is there some E0 which is a subset of the reservoir and also a subset of A0 so that I can halt? And the thing is, A0 is non-computable at all. It can be very, very complex. So you do not have access to it. So the formula is sigma 01 relative to A plus x and not relative to x. And so this is too complex. Because then you would obtain an A plus xe computation of S, and you would have no contradiction at all. So, well, here is the whole trick. Instead of asking for having one extension, we make an over-approximation. So we do not have access to this two-partition A0, A1. So instead of asking, can I find an extension for this A0, A1, I ask, for every two-partition, making as if they were the partition we consider, is there an extension so that I can halt? So it's another approximation. If the answer is yes in particular, this will be true for all particular two partitions, so this is good. So first of all, this formula seems much more complex because it seems pi1, you quantify over partitions. But there is one good property, is that by compactness, actually, this formula is sigma 0,1 relative to x. Because this formula is equivalent to asking, is there some finite set E so that for every two partitions of this finite set E, I can find a subset of one of the parts so that I have. So this can be translated into a sigma 0 x1 formula. So we have this over approximation. And so if the answer is yes, then this is good. It's an over approximation. So in particular, it works for auto partition. But what if the answer is no? Maybe the reason the answer is no is because of another two partition. Maybe the witness of failure is not all true to partition, but another one which has nothing to do with auto partition. And here is the whole idea. Since the pinch-hole principle, because partition is the pinch-hole principle, since this is a Ramsey type principle, we can say, okay, this is not a problem. We pick the witness of failure, and we commit to be a solution to both the original two partition, the one you want to be a solution, and simultaneously you want to be a solution to the other two partition, the witness of failure. And you know that as long as you will be a solution to the two, you will force divergence. So now you are done. You do exactly the same arguments with still your XCE set, and the argument works. So basically, the CGS argument is the following. So you want to build a solution G to a particular instance X of a Ramsey type principle. And you want to decide a property, which is basically a sigma 0,1 property, usually. So instead of asking, can I find a solution, can I find an extension for which I force my property, because my instance X is not computable, I do not have access to my instance. Instead of saying, can I find an extension, I can say, for every instance, can I find an extension forcing it? And if the answer is yes, we made an over approximation, we are good. If the answer is no, we commit to be a solution to both your instance and the instance witnessing the failure of the question, witnessing the no answer to the question. So this is the CGS argument. And, well, when I first saw the CTAPON argument and the CGS argument in general, I thought, okay, this is one way of building solution, but this might not, I don't see any reason why we should consider it as the framework for building solution to Ramsey type principle. But as it happens, this technique seems to be pretty accurate in the sense that we obtain often tight bounds to our questions. We can give a very precise analysis of the computability theoretic properties of Ramsey type principles. So, for example, I will exemplify with two theorems. So initially, I defined Ramsey theorem with two parameters. You have k, the number of colors, and n, the size of the n tuples for which you make the coloring. But you can add another parameter, which is the number of colors you allow in the output, in the solution. So initially, R was equal to 1. You wanted a homogeneous set. But you can say, what if I allow at least, at most, 2 colors? And so given a problem P, we can say that a set is P uncodable if there exists an instance of P so that every solution computes S. And we can ask, what set can we encode thanks to Ramsey theorem for n tuples and k colors? And Wei Wang surprisingly showed that for every n, if you allow sufficiently many colors in the output, so if L is large enough, then you cannot compute any fixed non-computable set. That is, given a non-computable set, you can always find, and given an instance of RT n KL, you cannot find a solution to your instance which still does not compute this non-computable set. So only the computable sets are RT n KL uncodable if L is large enough with respect to n. And L is exponentially growing in function of n. On the other direction, if L is small enough with respect to n, then you can encode any hyperarithmetical set. The reason is you can build instances so that all the solution will be sparse enough, so that if you look at the function which on n give the nth element of your solution, this will be a very fast growing function, and this can dominate the modulus of any function you want. And the modulus, every hyperarithmetical set has a modulus, so this is the way you show this. So the reason is just that you can build very fast growing function thanks to RT nkl when L is small enough with respect to n. And so there is some ongoing work with Peter, where we say, what if L is in between? Because there is a gap between saying L is at least the nth Schroeder number, so I don't know by heart the definition of a Schroeder number, but this is growing much faster than just the exponential. So there is a huge gap when n increases. And, well, and this was actually a reason why I thought that Ramsey, Mathias forcing and the CJS arguments may not be the right framework, because there seems to be a gap between the bounds we obtain. So it seems to be a coarse analysis. But, and so all of these results are proven by CJS arguments. But with some recent work with Peter, it seems that we are able to fill in the gap. And so there is an intermediary class, which is the arithmetic uncodable sets. So if we take L to be in between, actually you capture exactly the arithmetical ones. And so far we obtained some tight bounds in the sense that we know exactly for n small enough what are the divide lines. So this was an example of having a precise and accurate answer using Mathias forcing and the CJS arguments. Another aspect is that the CJS argument does not apply only to reverse mathematics. It applies to a lot of the computability theoretic frameworks for the analysis of Ramsey theorem. So, for example, another notion of comparison, so another way to compare two problems, is using the notion of computable reduction. So we say that P computably reduces to Q if, informally, if you have a Q solver, then you can create a P solver using some computable transformation of the input and the outputs. So more formally, every P instance computes a Q instance, so that for every solution to your Q instance, you can compute back a solution to your your P instance with the help of I. So this is a very natural notion of computability theoretic reduction. And you can see this informally as an implication. So P computably reduces to Q if Q implies P in reverse math, where you allow at most one application of Q. It's some kind of more precise analysis than reverse mathematics. And so the CJS argument still works within this kind of reduction. For example, we can say, so let's define a function to be hypermewn if it's not dominated by any computable function. So the notion relativizes, so you are hypermewn relative to x if you are not dominated by any x computable function. And we say that a problem P preserves L among k hypermeunities if for every k tuple of hypermewn functions and every computable P instance, you can find a solution Y so that at least L among the key fixed hypermewn function is still hypermewn relative to your solution. So in some sense, your instance, we have some non-computable solutions. So the solutions may defeat some hypermeunities, but it's weak enough so that it preserves at least L among k hypermeunity functions. And we can prove that Ramsey theorem for pairs and k colors preserves at least 2 among k plus 1 hypermeunities, but that Ramsey theorem for pairs and k plus 1 does not preserve k plus 1 hypermeunities. And this is a way to prove that Ramsey theorem for pairs and k plus 1 colors is not computably reducible to Ramsey theorem for pairs and k colors. So we can see that we have a way to obtain results of our computable reduction using these notions, and all of this is proven using the Mathias forcing and the CJS arguments. And we can be even more precise. So for example, if we ask, okay, maybe we cannot use one application, but if we allow multiple applications, so how many applications do I need to prove Ramsey theorem for pairs and 5 colors from Ramsey theorem for pairs and 2 colors? So we have a naive way to prove it, right? We first merge colors to obtain 2 big colors, and we make a first application of RT22. And then you obtain, in the worst case, 3 colors. So then you merge again 2 colors, you make another application of RT22, then you obtain 2 colors. And you make a third application and you obtain just 1 color. So with the naive algorithm, you can prove RT25 with 3 applications of RT22. But is it really needed? And actually, we can prove that this is optimal using the notion of preservation of L among K hypermunities. Because we know that RT25 does not preserve 2 among 5 hypermunities. So it means that there exists 5 hypermewn functions and a computable instance of RT25, so that for every solution to this instance, at most 1 among those 5 will remain hypermewn relative to the solution. And we know that, well, I didn't show it before, but Ramsey theorem for pairs can preserve 3 among 5 hypermunities, and it can preserve also 2 among 3 hypermunities, and and it preserves 1 among 2 hypermunities also. So it can preserve a lot of things. And so now, well, if you want to compute a solution to RT25, to this particular RT25, any such solution must have defeated at least 4 among the 5 hypermunities. So let's start. We start with 5 hypermunities, and then we make a first application of RT22. Whatever the application is, I claim that you can always find a solution so that at least 3 among the 5 functions will remain hypermewn. So, okay, let's make another application. And I say that whatever the solution is, we can still preserve at least 2 among the 5 hypermewn functions. So I know that I still cannot compute a solution to the RT25 instance. And I need to make a third application to defeat the last hypermewn function, and this is where you see that you need at least 3 applications. And it's interesting to see that in general, this gives you a tight bound in the sense that the naive algorithm for the application gives you exactly the exact number of applications needed. So the argument saying I merge colors and I make applications, this is the optimal algorithm. So CJS and Mathias forcing are really able to give very precise answers about questions around Ramsey's theorem. So, but everything is not perfect. We have some limitations. We have some open problems. And how much time do I have left? Oh, it's maybe one of the first time that I will use my whole hour, so I'm proud. So there is one example where this seems to fail. This kind of analysis seems to fail. So you can restrict Ramsey theorem for pairs, or let's say for pairs and k colors, to stable functions. So a function is stable, a coloring of the n plus 1 tuples and k colors is stable if, when you fix the n first components, you will have a limit behavior. So eventually the color will stabilize. And so we can define stable Ramsey theorem for n tuples and k colors to be Ramsey theorem for n tuples and k colors restricted to stable colorings. And there is also this computability theoretic notion, which is the notion of cohesiveness. So given a collection of sets, we say that an infinite set of integers is cohesive for this collection if for every such column, every such set, you are either almost included in it or almost included in its complement, so up to finite changes. And so you can define the cohesiveness principle to be, given any sequence of sets, you have a cohesive set for this sequence. So first of all, let's notice that stability for Ramsey theorem for n plus 1 tuples can be seen as Ramsey theorem for n tuples for 0 prime computable instances, because you can see a stable coloring as the delta 2 approximation of an n. So a stable n plus 1 coloring as the delta 2 approximation of an n coloring. And so in particular, stable Ramsey theorem for pairs can be seen as the statements for every delta 2 set. You can find an infinite subset in it or its complements. And actually, Ramsey theorem for pairs can be decomposed into cohesiveness and stability and stable Ramsey theorem for pairs. So I will just show one direction, how we obtain Ramsey theorem for pairs. So I will show the reverse implication. So given a coloring of the pairs and two colors, you can just define the collection of sets as follows. Rx is the set of y so that f of x, y is equal to 1. So now you can, thanks to cohesiveness, get a cohesive set for this sequence. And if you restrict your coloring to this cohesive sequence, then the coloring will become stable. So you have an instance of stable Ramsey theorem for pairs. So now you can apply assorti to 2 and you obtain a solution to your original instance. And so, of course, one question would be, is this decomposition non-trivial in the sense that is one of the two statements equivalent to Ramsey theorem for pairs? So for one direction, it's easy. Co does not imply assorti to 2. So I don't know who originally proved it, so I took the first paper in which I saw the results, but it's a simple proof. So it's, again, using Mathias, computable Mathias forcing and some simple weakness property. So this is quite simple. What is more complicated is the other direction. So those stable Ramsey theorem for pairs imply co. So this was a long-standing open question until it was solved by Chung, Salman, and Yang. So using some non-standard models and provably neededly non-standard, in the sense that the original attempt to make the separation was saying, well, we know that cohesiveness has a computable instance with no law solution. So maybe every instance of stable Ramsey theorem for pairs has a law solution, in which case we would build a model with only law sets. But I don't know all the course of this paper, but some people prove that there exists a computable instance of stable Ramsey theorem for pairs which has no law solution. So this attempt failed. But Chung, Salman, and Yang constructed a model of stable Ramsey theorem for pairs which contains only law sets. So how can it be? Just because the other proof required too much induction. And so if in RCNOT, since we restrict the induction, we could build a non-standard model where every set seemed low within the model. So it was answered, and Dennis, who worked a lot in this question, was unhappy that someone else answered it. So he said, no, this is not the right question we were looking at. Let's consider that it's still open. And so the true question was the following. We want to work on standard models. And there is a nice equivalence, a nice characterization of the standard models of RCNOT in terms of Turing ideals. So a Turing ideal is just what some people call, a Turing ideal is just a collection of reals which is closed downward under the Turing reduction and which is closed under the join, the effective join. And a model, so a structure is a model of RCNOT if and only if its second order part, so its collection of reals, is a Turing ideal, if the first order part is the standard integers. So we can define a notion of satisfaction. Problem P is, so a Turing ideal is a model of a principle if for every instant in this model, in this Turing ideal, you can find a solution within this ideal. And then this induces a notion of computable entailment that some people call omega reducibility. So P computably entails Q if every Turing ideal in which P holds is also a model of Q. And so the actual question was, those stable Ramsey for pairs, stable Ramsey theorem for pairs implies cohesiveness over computable entailments. Or in other words, does it implies it for the standard models of RCNOT? So this is the the big open question. And the reason it's so hard is that, well, all the proofs we know about stable Ramsey theorem for pairs is using Mathias forcing. And Mathias forcing, well, when you are sufficiently generic, it builds solutions which are also cohesive. So, yeah, so it seems that we need to find either a new technique, or we must make a finer analysis of the standard techniques. And we can also ask about the computable reduction, those cohesiveness computably reduced to stable Ramsey theorem for pairs. So this is almost the same thing. It's just that in the second case, you are allowed to use only one stable Ramsey theorem for pairs, while in the first case, you can make multiple applications. So this is often considered as like the big open question of reverse mathematics. For me, this is more the true question. This is how we found the right framework. And an answer to the previous question would also only be justified in terms of this question. So we want to have some general technique for answering questions, and this seems to fail so far. But maybe it doesn't necessarily mean that we do not have a sufficiently general framework, because we have other examples of questions which were open and were supposedly very difficult, and which have been answered with the same techniques, but just with a very careful analysis. Basically, whether ADS, so the ascending and descending sequence plus weak Koenig's lemma implies Ramsey theorem for pairs. It was a very difficult question, but it's still a CJS argument which has been able to solve this question. So the fact that we have failed so far with this technique doesn't mean that this technique fails. So, but this is the big question. Like, does this R32 versus co question witness a failure of our current framework, or is it just because we haven't found the right proof yet? But what's nice about this question, so the previous question, is that it yields a lot of purely computability theoretic questions, and so which are interesting for themselves. So first of all, we can ask, is there a set so that every infinite subset of it or its complement computes an OR cohesive set? And equivalently, we can ask, is there a set so that for every infinite subset of its complements, every infinite subset of it or its complements has its jump of p a degree relative to 0 prime, because this is exactly the power of computing a p cohesive set. A second question, which would be a strong implication, is there a set so that every infinite subset of it or its complement is high? So we do not know the answer to this question. We know that if the set X is delta 2, then we can always find a low to H. But if we take X in absolutes, we do not know whether we have an instance which has only high solutions. So if the answer is yes, then it would give a partial answer to a previous question. But in any case, I think this is an interesting purely computability theoretic question. And the last, a last theoretic question is about the jump uncodable sets. So we say that a set is P jump uncodable if there exists an instance of P so that the jump of every solution computes S. And we ask, so this is a technical way to ask it. So are all the RT12 jump uncodable set precisely the 0 prime computable ones? The best way to think of it is, given a non-delta 2 set S, can I always find, given a non-delta 2 set S, and given an arbitrary instance of P, can I find a solution to P so that the jump does still not compute S? So this is some kind of cone avoidance, but relative to the jump. And so we don't know the answer to this. Morally, I would tend to say yes, but the standard techniques have failed so far. Okay, so to conclude, we really have some pretty good framework to answer a question about Ramsey type principle, and it's quite minimalistic. It's just Mathias forcing CJS argument, so we sometimes have to make some very subtle applications of it, but it's always the same idea. And so this can be taken as an evidence that we have found the right framework, especially because we obtain accurate results, we obtain tight bounds, and we have still these big questions, and which would be especially interested if it revealed the failure of the standard technique. So this is the end of my talk. Thank you for listening. Yeah.
I thought, has anybody ever asked a question about this kind of global structure? I mean, is there any infinite chain or something?
So there is an infinite decreasing sequence because Ramsey theorem for, let's say, pairs and so k colors and L. When you increase L, this weakens the principle strictly. So you have an infinite decreasing sequence.
Go this way.
Yeah.
Go this way.
This way, that's a good question. I don't know. I would tend to say yes still by the same witness, but you variate both N and L so that they become incomparable. But I don't know so far any such example. I guess we could construct some very artificial one, but among the natural instances, we do not have one yet. Yeah. And of course, you have some infinite increasing sequence. But yeah, there is no global structure that we remark about the zoo. Yeah. Yeah. Yes, and especially because if we really wanted to say something significant about the structure of the zoo, we would have to, I guess, start considering very artificial statements. It wouldn't be anymore the analysis of ordinary theorem, but of any kind of theorem and of any kind of statements.